All right, gang, Mr. Spencer here. We have spent some time talking about Newton's second law of motion, and especially we've been talking about the relationship between force, mass, and acceleration. Today, after we do a little bit of review, I want to go into just some very basic calculations using Newton's second law. So before we do that, let's review. All right. Remember, when we talk about this relationship between force, mass, and acceleration, what we're doing is we're talking about net forces. So whenever I have an unbalanced force, we have a leftover force, which is called a net force. If I had a balanced force, that would mean that we wouldn't have any leftover forces, so there would be zero net force. And as we start talking about it, we want to understand that objects are going to accelerate in the direction of the unbalanced force. So if I look at this one right here, okay, this has a force due to gravity of 800 newtons going down and a force of tension of 1200 newtons going up. Well, that means there's going to be a net force or a leftover force of 400 newtons going up. All right, similar to this one right here. Here we have air resistance going upwards of 600 newtons and the force due to gravity of 800 newtons. So that means we are going to have a net force of 200 newtons going down. So it's going to accelerate downwards. And in this one, all right, we have a normal force going up of 50 newtons, force due to gravity or weight of 50 newtons. So those cancel out. Excuse me, those are balanced. But we have this force of friction of 20 newtons to left. So that means that we are going to have a net force of 20 newtons to the left, even though there's three of those. All right. So in the past few days, we've been talking about these relationships between acceleration and force and acceleration and mass. And we did some experiments where you got something similar to this, where if you compare the force to the acceleration, it will go up like this. So that what we're saying there is that acceleration is proportional to force, meaning if I increase the force, I know that the acceleration, or if I increase the net force, the acceleration is going to go up. Likewise, if I know that my acceleration is going up, I can tell that it's because there is an increased net force. Mass is different, okay? Acceleration is inversely proportional to mass, meaning if one goes up, the other one goes down and vice versa. So if I have an object with greater mass, then that means my acceleration is going to be less. And if I have less mass, it's going to be easier for me the acceleration is going to increase. And that's where we get this idea of acceleration is proportional to the force divided by the mass. So let's do some examples here. Like if you've got this kid, okay, is getting pushed around, his mass is staying the same, all right? But he's going to accelerate directly proportional to the force. So if I push him with greater force, he's going to accelerate more. If I push him with less force, he's going to accelerate less. So once again, force and acceleration are directly proportional. However, if I have acceleration and mass, that means that acceleration is going to be inversely proportional. So when one goes up, the other one goes down, and they are in opposite directions. So let's take a look at this one right here. So we've got this huge gun right here going off, and let's compare what's happening to the gun and to the bullet. In both cases, Newton's third law, all right, they're experiencing the same force. But the bullet is going to accelerate a lot more than the gun. Well, why is that? Well, that's because the gun has a greater mass. All right? The gun itself has a greater mass, so it's going to accelerate less. But the bullet has less mass, so that same force is going to cause that bullet to accelerate more. All right, so let's kind of take a look at those, do a few little conceptual questions. All right, if I have a cart and it's on a frictionless surface, we'll just pretend that that's how it is, and it's accelerating at 0.35 meters per second every second, and I'm pulling it with 2 newtons of force, how fast is it going to accelerate when it's pulled with 4 newtons of force? Well, in this case, we have the mass staying the same, and then we have acceleration and force. So because force and acceleration and force are directly proportional, if the force increases, so does the acceleration. So if the force doubles, the acceleration is going to double. So I would end up with an acceleration of 0.7 meters per second every second. All right. Another example would be if I have a fourth of a kilogram cart on a frictionless surface. It's accelerating at 0.5 meters per second every second when pushed with this force. How fast is it going to accelerate if you have a 0.5 kilogram cart that's that's being pushed with the same force? All right. Well, this is one of those examples of the force staying constant, but the mass is changing. And because acceleration and mass are inversely proportional, meaning when one goes up, the other one goes down, that means if I double the mass, the acceleration is going to go down by half. All right, so that's when we started out with 0.5 meters per second every second for the acceleration. If I double the mass, I end up with half the acceleration as before. So here's the new stuff. Let's go over the equation for Newton's second law of motion. Okay, so we talked about this idea of acceleration being proportional to the net force over the mass. All right? And what we can do is we can change that into this equation of net force equaling mass times acceleration. So remember, we measure force in newtons, and a newton is just how much push is necessary to get 1 kilogram to accelerate at 1 meter per second every second. With mass, we're measuring that in kilograms, and acceleration, we're measuring that in meters per second, or meters per second squared. So what we're saying here with Newton's second law equation is that the net force that's acting on an object can be calculated by multiplying the mass of the object by its acceleration. So once again, what we get is this equation right here, where the net force is equal to the mass times the acceleration, or F equals ma. All right, so let's do 3 examples really fast, and then we'll be good to go. All right, so here's the first one. If I want to find the net force, well, the question is, what's the net force required to accelerate a 2 kilogram mass at 3 meters per second every second? Well, I've got this 2 kilogram mass. It's going to accelerate at 3 meters per second every second. What's our force? Well, I know that if I have mass and I have acceleration and I'm looking for force, I can set up the equation to be force equals mass times acceleration. So the net force is going to be 2 kilograms times 3 meters per second gives us 6 newtons. And this is where some people sometimes say, wait a second, okay, if I've got kilograms and meters per second, how do I get newtons out of that? Well, remember, a newton is how much force is needed to make 1 kilogram accelerate at 1 meter per second every second. So if I take a kilogram, multiply it by meter per second, I get 6 newtons, or I get newtons. All right, so that's how that works. Now, this same equation can also solve for things like mass. All right, so if I have an object that's being pushed with 100 newtons and it's accelerating at 5 meters per second squared, how would I figure out the mass? Well, I know force, I know acceleration, I'm trying to find mass. So I can take force equals mass divided by acceleration and just solve for mass, which gives me force divided by acceleration. So if I take 100 newtons, divide that by 5 meters per second squared, I'm going to end up with 20 kilograms. And just as a reminder, this is how we get newtons and meters per second squared and end up with kilograms. Okay, last one. If I am trying to find the acceleration of a 10 kilogram mass that is being pushed by a 5 Newton force, same idea as before. I know what the force is, I know what the mass is, and I'm trying to find the acceleration. And I just use a little bit of algebra to manipulate this, and I end up with acceleration gives me force divided by mass, and I get 5 newtons divided by 10 kilograms, which gives me 1/2 meter per second squared. Whew. Okay, that's a lot, But the main idea here is that we want to understand that acceleration and force are directly proportional. When one goes up, the other one goes up. When one goes down, the other one goes down. Acceleration and mass are inversely proportional, so they go in opposite directions. And we can use that to give us this equation of the net force equaling mass times acceleration, and you should be able to solve for any of those variables. All right, I hope that made sense. If you have questions, just let me know.